All right, so the story started something like 2 years ago when there was a workshop at the Curious Hospital, which I went to, and the guy organizing the workshop, Xavier started, and so the workshop was on uterus cancer, and he started his talk by saying 2 things. One thing is that 1 woman out of 3 has the papillomavirus, and papillomavirus is known to be responsible for this kind of cancer. Even though maybe 1 woman out of 100,000 will eventually develop a tumor. So, which means that women can very well live the whole lifespan without any problem, even though she will have that virus. And what biologists say, or doctors say, that this virus may stay dormant for a lifespan, and for some odd reason will all of a sudden decide to wake up, and bingo, it goes bad. And somehow for physicists it's not really satisfactory. I mean, how come we might imagine scenarios where viruses could, stay dormant and then wake up, but not really satisfactory in a sense. And then the second thing he said is that 100% of the tumors would show up at the interface between 2 epithelia. So the 2 things put together for physicists, it right away rings a bell, because if you look at the way bubbles nucleate in a glass of champagne or in a glass of beer, or if you look at how vortices nucleate in superfluid helium, and it's a wide class, so they always nucleate much more easily at interfaces than in the bulk. I mean, heterogeneous nucleation by and large is much easier, orders of magnitude easier than homogeneous nucleation. So immediately I decided that maybe it has something to do with the nucleation process. And Jean-François Joanny, with whom I'm doing most of my work, attended also the workshop, and then we started to talk together and decided maybe it's time to work in that, try to do something in that field. And I went to Xavier, and I gave him a tutorial about nucleation processes, and he kind of liked the ideas, not for that problem. Actually, he was not convinced for that problem, but for some other reason that for statistics they had at the Curious Hospital, he thought it might be relevant. And then for more than a year, he gave us courses on tumors, growth, and so I did also with book and so on. And so what I'm going to talk about today is part of Marcus Bazan's thesis, and I'll show you some simulation done by Jens Algeti, and I'll say a few words about something we are starting with Jonas Hans. And Thomas has been helping us in all the aspects of the work. And now show, if I'm not too slow, I'll show you some experimental results that we start to have with Fabien. So these are very preliminary results that Fabien is getting in collaboration with Daniela Minkiewicz and Giovanni Capello. So now, upon reading and learning, we bumped into also something which is called metastatic inefficiency, which we thought might have some relevance, and I'll come back on that. People know very well how to invade, let's say, the liver of a mouse or the lung of a mouse, in that case it's a lung, by 100,000 cells or so, and look at the outcome of the cells. And it turns out if you can follow the statistics, and the cells may duplicate, start having aggregates which grow, but eventually they may shrink back and disappear, and only 1 out of 1,000 cells will eventually succeed in making a tumor. So metastatic processes are very inefficient, fortunately for us. But and this statistic also gave us some more argument or some more incentive to try to do something in that field. And let's start with the Gedanken experiment. So suppose we are able to make a chamber, and this chamber has walls which are perfectly permeable to nutriments, growth factors, but are rigidly solid. And we close the chamber on one side by a piston, and this piston is connected to spring. And we see the chamber with the duplicating cells, and we wait. So after some time, the cells start to duplicate, and at some time they start to push on the piston, and they push more and more, and at some stage the piston will stop. And it will stop, and that will define a force. The compression of the spring will define a force, and dividing by the area, it will define a pressure, some kind of pressure, but it's not hydrostatic pressure because the fluid can flow freely through the walls. So it looks more like osmotic pressure, but it's not an osmotic pressure. I'm sorry, it's just jet lag. It's not an osmotic pressure either, because the ions can flow and so on. So it's a mechanical pressure connected to the tissue itself, for instance. And why is it pressure? So we call that homeostatic pressure, or steady state pressure if you prefer. And why is that concept important? And it's something which could have been introduced years and years ago, and somehow we didn't see it. It could be done in 2 dimensions as well, but let's keep that. Let's also look at just orders of magnitudes. From all the work we've done in cells and which have been done by others and so on, we know that cells can develop effective pressures either from the motor activity or from the polymerization, depolymerization of actin type of activity of the order of 1,000 Pascal, 10,000 Pascal. So we expect these cellular pressure to be of the same order of magnitude. We might be wrong by, I don't know. But it's just, a naive expectation, let's say. And if we were to do that in 2D, for 2D epithelia, it would give two-dimensional pressures which would be in the same ballpark as 9 ppm. So they would be also measurable. Okay, so back to why is it an important concept? Is that suppose now that we take 2 chambers and a mobile piston here, and this piston does not allow, first we assume that the piston does not allow for biochemical torque between the 2 tissues. And so it's only mechanical interaction that we want to discuss. And let's say the tissue in the right part here has a lower steady state pressure than the tissue in the left part. And we let the tissue duplicate. And so at some point, so the pressure grows. And at some point, pressure in the right compartment will reach the steady state value of the right tissue here, which means that the number of apoptosis and number of duplication are equal. But this guy has a pressure which is lower than his own steady state pressure. So it keeps on dividing. So the pressure raised, and now the number of death of the cells is larger than the average number of the duplication. So this piston moves to the right. But this guy still has a pressure which is lower than its steady state pressure. So the piston keeps on moving, and there's nothing preventing this tissue to totally invade that tissue, and there is no compromise. So the one tissue which is a larger steady state pressure will always, under those conditions, if there is no signaling, and if the biochemical conditions are the same for the 2 tissues, then there will be no compromise between the 2 tissues, and this tissue will always wipe out this tissue. And so this mechanical unbalance, I think, is really crucial to understanding the question of tumor growth. Now for what? Let's allow for some kind of signaling for a few seconds. And suppose that let's call the tissue which has a lower steady state pressure, the healthy tissue, and suppose the healthy tissue is able to send a signal in the cancer tissue, let's say, here, which locally decreases the steady state pressure of this cancer tissue. So now you see that if this compartment is very big, and the signal here will never propagate any further than a few cell diameters. So if the chamber is really big, everything will happen as if there was no signaling. And so this tissue will wipe out this tissue. In the inverse, if the chamber is very small, and if it's small enough that you only have the part which is influenced by the healthy tissue, now the effective steady state pressure will be smaller than this one, and now the healthy tissue will totally wipe out the cancer tissue. So you start to see that there is a length scale at which, and then there will be an unstable steady state where the size is such that these two guys balance. So the space average of duplication and cell death is balanced, but it's an unstable, as you can see from this argument, it's an unstable steady state. So you can start to see that there are mechanisms which could give you unstable steady state and a critical length scale to exceed if you want a successful growth. It turns out this is not a scenario that you see in nature for a very simple reason. Cancer is an evolutive disease. And those mutations which are successful are those mutations which take advantage of the surrounding world. So those mutations which would not take advantage of the healthy tissue are not successful. It's not to mean that it does not exist, but this will die out automatically, basically. So it's not, if you read the books, and it's never, I mean, they tell you that in fact, the cancer tissue picks the growth, the factors from the normal tissue. So this is exactly the control which is occurring. So there's no length scale there. Okay. Now, do you want to describe if you want to describe the growth process, of course, there are source terms for duplication and that, but also you want to describe the tissue as some, I mean, maybe a foam, maybe a solid, maybe a liquid. And in fact, there is an extensive literature dating back from very early, I think, Steinberg, showing that for most tissues, maybe not true for all tissue, but true that for most tissues, they behave like liquids on time scale of hours. So even on time scales shorter than duplication and death rate, tissues behave like tissues mostly, and they can chop off tissues and mix, I don't know, different type of cells. And first you see that they make very spherical shaped drops, which shows there is an interfacial tension. And now they can sort out, so it's two different tissues, I don't remember exactly which is which. And again, they can measure and show that interfacial, they separate out according to interfacial tension, and they can measure the interfacial tension. So we know these numbers. And we know, basically, we can also know the viscosity, if you want, of these tissues. Now, for some, okay, let me show you a video done at the Cure Institute by Karen Gevorkian and François Brochard's group. So they pull on an aggregate of cancer cells. So these are murine sarcoma cells, and in fact they increase the sucking pressure by, if I remember, 1,000 Pascal. So it's 5 times, and it's over a 5-hour span. And you see it really flows, and you also see the fact that there is a tension there.
What is the size of this tube?
It's a capillary. Okay, you know the size of the cells. Cells about 20 to 30 microns, and you see that 1, 2, 3, 600 micron diameter. Okay, this is another video. So it's in a longer time scale. So you see that you have cells, duplicating cells here. So maybe it's a few days. And you see, again, they make droplets, and the droplets fuse. So it's like dew. I mean, if you look at a growing dew, you see almost the same thing. But it's just the scales are totally different. Now, it turns out in some other cases, the fluids don't flow. And there are beautiful experiments on epithelia done in Santa Barbara, which show that for some of the epithelia, the cells don't move with respect to each other, aside from duplication and apoptosis events. They can follow that very nicely over a longer time scale. And so my point is that even if you are in that case, so if between duplication and apoptosis events, the cells don't move with respect to each other, so it's essentially an elastic medium at short time scale, even in that case, at a long time scale larger than duplication and apoptosis rate, it will still behave like a fluid. And the argument is very simple. So I didn't put any cancer indices, but you could do it. If you have in an elastic medium, you can write something very similar to what you write in electrostatics. That is, the stress can be written in terms of the displacement field and a polarization, so an elastic polarization field, which is due to the local sources of deformation that are outside the description range of the elastic field here. And typically that's what happens if you have a duplicating cell or a dying cell. So locally, a duplicating cell will give you a local stress, which is something different from the rest of the tissue. And the difference now with electrostatics is that what can be easily connected to what you know is that is to the rate of the duplication rate or the apoptosis rate is the time derivative of this polarization field. It is elastic polarization field. So now, with that and this relation, the constitutive relation links the derivative of the stress tensor to this duplication rate here. But these rates depend on tension. So if you're close to steady state, and this is the real equation to be used, real constitutive equation. But now if you're close to steady state, you can linearize this equation. And if you linearize this equation, you wind up right away with the Maxwell expression of a gel, which tells you that at short time scale, it's an elastic medium, and at long time scale, it's a fluid. So even in that case, long time is a fluid. So, and we are back to the physics of fluid in a sense, and you can write now with one very important difference. And this important difference is that the density, so cell density is not conserved. And there is a source term with the duplication and apoptosis. And that's basically it. So we can come back to the piston case, but that's not so important. Let me skip that and let me show you some simulations. So you can mimic cells by giving you some rules, like let's say the usual rules that people use for fluids, but you add up the probability of a cell to disappear, so a molecule, let's say, to disappear, and another probability of that molecule to appear, or to duplicate. And if you do that, you wind up, let's say, start with a simulation of having an aggregate experiment. Oh, that's too fast. I did something wrong. Where is it? Let me just start again. Sorry. What did I do? I lost control. Shit. What?
Try clicking on the badge on the move it. It's not.
What?
What do you want to do? You want to move the.
I want to move it, yeah.
Try clicking on the.
No, I lost total control of that.
So you cannot do anything?
I cannot do anything. Shit. Wow. I can just turn it off and on. Okay?
Instead of language, have all sorts of stuff that simulation.
It will take a few minutes, but that's
You cannot go back to the talk?
what.
You cannot go back to the talk?
No, let me just. I'm sorry for loss of time. No more than that. Okay, so I hope I can show you the videos. But anyway, so you can, with these equations at hand, you can raise the question: what happens if I put one cell here which duplicates faster than the surrounding tissue, and if you don't do it, I mean, if you just raise the question the way I did. And so you just balance the stresses at the interface, and you just have different duplication rates and apoptosis rate. You find exactly the same thing as in the Gedanken experiment, is that this tissue which has the highest steady state pressure will always wipe out the other. And it's just don't get to that. Now, I showed you that it's known that tissues have interfacial tensions. And so, upon in discussing the problem, just balancing stresses, we ignore surface tension. So what happens if we introduce that surface tension? And you see now that the pressure in the tissue which is inside the aggregate is the pressure outside to which you add Laplace pressure. And now you can have a tissue, let's say normal tissue, which has a lower steady state pressure than the growing tissue, but because of the Laplace pressure, the pressure inside the growing tissue is larger than the steady state pressure of the growing tissue. So even though this tissue would grow if there was no tension, now the tension inside is larger, and so the tissue will shrink, as a matter of fact. And it's only beyond some critical value, and that critical value is simply defined by the fact that the difference in pressure is just the steady-state pressure difference of the two tissues, and that defines for a given tension a critical radius. And above that critical radius, if tension is constant, above that critical radius, then the tissue will grow, and below that critical radius, the tissue will shrink. So you do find this this idea of a critical radius, not because it's a first order transition, but just because of the rules of the mechanical rules of the growing tissues. Now, these tensions need not be really constant. It could be, in some cases, it could be that this tension grows with the radius of the aggregate. And if it grows faster than the radius itself, now what I described as a unstable steady state could become stable. And we explained and we discussed that with Xavier Sast, so the doctor. And so our idea that in those cases, the tumor might be benign. I mean, they would stay at some stable state at which the tension would adjust spontaneously. And then he said, oh wow, now I understand why the doctors, when they cut open the tumor, if the tumor pops open, they say it's a benign tumor. Of course, they send it to histological analysis, but they right away know that it's a benign tumor, and that might be the reason why. I mean, these benign tumors are under pressure. If instead, when they cut it, it doesn't pop at all, then they know it's more serious. Now, okay. So, and if the problem was just mean field problem, the way I've been describing it, we would never have a tumor, because it's known that cancer, this microscopic tumor, are monoclonal, so we know it starts from one cell, and this one cell might very well always be smaller than the critical radius you have to achieve. So it means that one has to deal with the statistics of duplication and apoptosis. And because it's monoclonal, the statistic actually is simple. So you can write a Maxwell equation. So I mean, there is a probability for a tumor of size of a given size to get one more cell. So it's connected to duplication rate, or it could lose a cell by apoptosis, and all that is fairly easy to write. And you just have to take some care in writing the pressure dependence. And the pressure dependence boils down to the 1 over n, so number of cells to the 1/3 dependence. It's just relating to the radius to the total number of cells. So it's simple, a very simple way of writing the thing. And just open your favorite statistical physics book. I mean, what you want to know is the probability to exceed this critical radius. So it's called splitting probability. Take Van Kampen book if you like it, and you get the result. And you can also do simulations. And here is a typical curve. So we know interfacial tensions. We know the average division and apoptosis rate. We don't know the steady state pressures. So there we have to make guesses. And we don't know how this the pressure dependence of the rates, and there also we have to make guesses. But so we do make guesses, and here is a typical curve that we get. So one, say the continuous curve and the analytical curve of points or simulations, and so in that, with the number that we chose in that case, you find, and actually we adjusted it in such a way that they look like what is known from the experiments I've been showing you at the beginning. And so in that case, you can see that for a critical size of 10 cells, you get a 1 out of 1,000 probability of success, and which is what is observed. So But also what you find is that's what's more interesting is that if you change the interfacial tension just by a factor of 2, you change the probability by 5 orders of magnitude. And that also we know, of course. I mean, it's not a surprise to a physicist, but it may be a surprise to a doctor. And so I think it's very important. And it does, in fact, it may explain something which has been known for a long time, which is that some metastases are known to succeed in some tissues, but not in other tissues. Okay, so I'll jump. And it may also explain of course, why the tumors arise at the interface. This is more general than just the uterus cancer. Tumors very often arise at the interfaces. And of course, just by the very naive argument of that time, you see that the critical number, if you have an interface, rigid interface, then it's essentially divided by 2. And if you just look at this curve and you start from a critical number of 10, divide by 2, get to 5, you find the probability is 10 times larger. I should say only 10 times larger because in nucleation events it's very often much larger effects. So it's maybe actually it's maybe an artifact of the neighborhood eventually. But even 10 is important because it makes a difference between 10 years and 100 years. Okay, so let me just add, so maybe if the tumors are successful, they grow to millimeter size, and at this millimeter size, they reach a steady state. And the steady state is such that in this region here, outside, the cells divide, and they divide because they get the growth factors from the healthy tissue. And in this region here, they just move toward the center, but they don't do much. And they die in the center. And this steady state may also last for years and years. And it's only when you get the next instability and that angiogenesis takes place, so that blood vessels invade this tumor, that then it gets really bad. So we can get the steady state. We didn't work out the instability in the angiogenesis case yet. But let me just jump on that because I'm late. Let me just. That's one very easy way to discuss this steady state is by assuming that the duplication rate and apoptosis rate are directly controlled by the growth factor and the oxygen content. In fact, the core where the cell die is defined by a lack of oxygen. It's called hypoxia. It's well documented. So just do that, you find that the size of this tumor is about 3 times the length scale over which oxygen can penetrate. So, okay, now the most important is that if all of that is true, we must be able to do experiments. And we are starting to do experiments, and what we do is just take cell aggregates, cancer cell aggregates, we squeeze them there, and we look at the diameter as a function of the pressure on which we apply on the plates, on the side walls here. And but these walls are permeable to both nutriments and growth factors, as in the Gedanken experiment. But here we have to be more careful because the length scale I just introduced before played a role. Here, this is the millimeter size, and so there is a length scale over which the nutriment penetrate, and in the middle this cell do die, so there is a hypoxia in the middle. So we have to take account of all that, which we are doing now. And these are preliminary results, and I just want to show that very quickly, that if you don't put any pressure, and you start from any value of any number of cells there, that goes to some kind of steady state here, which depends on the nutriment and so on. But now you exert, tiny pressure, 3 Pascal, and it already loses something like 100 micron diameter. 30 Pascal loses 200 micron diameter. 300 or 400 Pascal, now it loses 400 microns. And now if you, for instance, in that case, for the 30 Pascal, you wash out and you put the nutriment back, and it goes to the steady state without pressure. I'm sorry, you turn the pressure off, and it goes to the steady state without pressure. So it's really a steady state. And now if you exceed, so here is 16 kilopascal, and you see it goes back to the original size, but and if you exceed slightly this value, it all collapses. So you do, just by playing on pressure, you can suppress a tumor. So now we are in disentangling experiments because you have to calculate the shape and so on. And we do see that this notion of pressure is there. We can start to put numbers, and it's fun to see. I mean, if you squeeze a liquid drop, it gets wider. Here you squeeze the liquid drop, the cell aggregate, it shrinks. Okay, thank you for your attention. Yes, I'm listening.
I was wondering about this popping that you were talking about when they remove tumors.
Yes.
You say that the benign tumors they're the ones that pop. So is the pressure, is this popping because of the pressure from the healthy cells that are? I don't really understand.
It's popping because you have if you look at the benign tumors, there is a strong layer of tissue, or it's not really tissue, a strong layer separating the normal tissue from the tumor. And so it's it looks like a solid surface which separates the two tissues, and which is able to exert a strong pressure, strong Laplace pressure. So it's not just like a balloon. It looks more like a balloon than like an interfacial tension of two fluids. Yes?
So you said that because the tumor is monoclonal, kind of ignored the heterogeneity, but I mean, I think there is some sort of cancer thing, like this heterogeneity in cancer, like sort of isogenic heterogeneity in cancer has been sort of brought to light, and people say it's one of the most most significant effect of the success of metastasis, actually how heterogeneous are the cells within it. Do you think it fits in your model?
Yeah. I mean, eventually, of course, a tumor to be successful, to become large, you need about 6 different mutations. But what we are speaking of here is just the very early stages when it's small, when it's a microscopic tumor, and there it's known to be monoclonal. But this is the only early stage. I mean, this is the early stage. But for instance, to get to the angiogenesis stage, you probably need some more mutation and so on. So there are other mutations. That's true. But at this early stage, not.
question.
Or maybe they're not fundamental.
So I was wondering, how sensitive are your results for the nucleation of these tumors to the details of the interaction between cells? And the reason I ask is because, for example, with Boris's tissues, you know that the system is basically solid-like except for the proliferation, which allows the tissue to be liquid-like. But there are other types of tissues which are sort of liquid-like even in the absence of proliferation. So in other words,
that's
how
what they said. Yes.
Yes. So in other words, how sensitive is the details of this nucleation process to the details of your model for how the cells interact with each other?
They are very sensitive, and that's a point. I mean, usually you don't like your result to be sensitive to, you like the result to be robust, but it's no. It is not a surprise to physicists. I mean, nucleation processes, in that case, it has nothing to do with the first order transition, right? It's really connected to the fact that it's a system it's a non-conserved system. But it's known, we know that nucleation depends on tiny details. And that's what makes, in fact, what makes the problem difficult. Because this nucleation barrier here can be biased by anything. So all these, say, you have a chemical, for instance, some chemical pollutant, and it changes the barrier a little bit. And then this changes the outcome tremendously. So, and then all of that is there.
So how are you sure you have the right cell-cell interaction model? How are you sure that that's what you have is the physical sort of mechanical interaction?
Or you mean in simulations?
Yeah.
Very naively for the time being, very naively. We just adjust the numbers in such a way that it looks like the experiments. Right? I mean, the important thing is not so much, simulation tells us that it looks like the calculation and that's all, and there's some, it allows also to discuss some fluctuations, but it's terribly naive right now, but we can't do any better. But I think the important message is that first, it depends on all details, which is something we don't like. I mean, usually I don't like that too much, but this is life. We can't escape that. And there is things to learn from that. And second, maybe it gives an idea on and it may take a long time to diffuse in the doctor community, but the one way to fight cancer would not be to kill. I mean, what do people do now? They just try to kill the cancer cell faster than they kill the normal cell. Right? So you play on the apoptosis rate. But it would be much nicer to be able to crank up the steady state pressure on normal tissue, and things would happen just by themselves, or crank up interfacial tension. So there are ways. I mean, and it may take a long time because we have to learn, and this is just the real problem has many other dimensions. But I think we cannot avoid addressing the mechanical part of the question, and this is just a way of starting to address this question.
Are there two separate issues? One is phase segregation, and then one is nucleation. I mean, is it necessary that the two components segregate? Could you have cases where the cancer grows without there being this two-phase behavior?
So you're right. I mean, it seems that at least for the small microtumor, they do phase separate. But of course, those which don't are more dangerous. But so I mean, they probably exist, and these are the most dangerous. So suppose that some are able, since we have mutations, let's say, first mutation, it divides faster, okay, but there is a tension. So test difficulty, this nucleation problem. Second mutation, successful mutation, you decrease the tension. And you set it to 0 or even negative values. Then it's a lot more dangerous. So all these questions are there. All these questions. Wetting angles, all of that. I mean, this is just a very little start, but all these physics are there. And connected to mutation.
Is it known experimentally that the steady-state pressure of healthy tissue is smaller than that of tumor tissue? I mean, this is the basic.
Nobody ever measured it. We just are starting to measure it. People. So the most that people have done is put cells in gels and get to a steady-state shape of the aggregate in the gel, and from the gel deformation they can infer the mechanical stress that this tumor has been exerting on the surrounding. But this is a regime, in fact, where you have duplicating cells at the outside and dying cell in the inside. So it's not a measure of the steady-state pressure. So, we do get some orders of magnitude for this kind of experiments, but this is not enough to extract the steady-state pressure. So we don't know. So if it turned out that it's the contrary, we are stupid. Okay? But we'll see. That's what theory should do.
Do tumors ever buckle because of the necrotic cells on the inside? And if they were to, would that affect like their growth or whether they...
Tissue buckle. Tissue do buckle and invading tumor. We are doing some calculations where it's obvious that it's just in buckling instability. I mean, for the physics, when physics looks at, when Xavier was showing us pictures, and we just said, wow, this is buckling. Yeah.
So we should probably thank the speaker again at this point.
So I apologize for the video.
Should I stop here? Tell you about another tissue where the local mechanical properties are important. So this is cartilage. These are some of the absolutely stunning images that we've gotten in our lab. It's a beautiful tissue. It has a depth-dependent structure, and for that reason, we sort of got into the game and started working with people in the mechanical engineering department to try and measure those properties. So, if my presentation will go to the next slide. Okay. So we all know about cartilage. It's the tissue that coats the bones in our joints. We know actually quite a bit about the gross mechanical properties of the tissue. It's viscoelastic, and in the right geometries or the right compressions, pore-elastic. We know it has a depth-dependent structure, and we know a lot about the chemical nature of healthy and diseased cartilage. Despite all of this, we know actually very little about the local mechanical properties. Okay, and we know, for example, that there is a depth dependence to the concentration and orientation of the different components that make up the cartilage. And so, for example, near the surface, you have collagen fibers that are arranged parallel to the surface. Near the bone, they're arranged perpendicular to the surface. They form the extracellular matrix. There are cells, and there are these proteoglycans, these charged sugar molecules that essentially hydrate the tissue. And we know a little bit about how cartilage absorbs shocks in compression. So the idea is that this is sort of an old, I guess, one of the oldest versions of a shock absorber, where if you try to compress the tissue, the water has to flow out through a porous network. And so then you have some time scale for that fluid to come out, and so you get a very pore-elastic-driven phenomenon. So, we've been interested in these kinds of shock absorbers for a long time, ever since we've had stagecoaches and buggies. Here's an example of a slightly less old, but still, fairly old shock absorber. Here you had some mechanism that translated vertical shocks into friction, And then the modern shock absorbers actually work very similarly to cartilage. They have these little holes in one of the pistons through which the fluid flows, and that sort of defines the time scale of the proelasticity again. But it turns out that if you look at cartilage, the main failure mode for cartilage is shear. And so then you start thinking about, well, how do we think about shear absorbers? So this is like a really old one. This is the mausoleum of Cyrus the Great. And the idea is that this mausoleum was built on very smooth stones. It's in Iran, which is prone to earthquakes. And so when the earthquakes hit, the mausoleum actually shifts on these smooth stones. And that was the idea then. These days we'll have buildings actually sitting on top of shock absorbers, or I guess shear absorbers, where the outside is made out of rubber and the inside is actually made out of lead. And then when an earthquake hits, these things end up taking up all of the strain, and then the building on top doesn't move at all. So what we want to do in our lab is ask a little bit about how does this kind of shear absorption happen in the tissue. Okay, so we take cartilage tissue from the patellofemoral groove of a young cow. We dye it and treat it with antibacterial, with antibiotics, and essentially then put it in some salt solution. We then look at the tissue in our shear cells. So the idea is that if I have a tissue, which here's the surface, here's the bone, I take it, I put it on its side, and in my shear cell I move one of the plates back and forth, and I measure the force on the other plate. And then I look below at the tissue, and the idea is that any parts of the tissue that are softer than another are going to end up being are going to end up straining further. Okay, so parts of the tissue that are stiffer are going to have a much much lower strain associated with them. So here's the kind of thing that we see. So this is a video. Let me show you what it is that you're looking at. These dyed parts are the cells. This part is the surface of the tissue. About 5 pictures like this below would be the bone. All right? And so the idea is that if you take a look at the movie, this is a looped movie, at the very beginning of the movie, what you see is that the cells near the top move faster than the cells below. But towards the end of the movie, everything starts to move together. Okay, so I'm going to repeat that a couple of times. Yeah?
What's the dye?
The dye is something that they had on the previous page. I don't know what it is. Let's see there. Blah, blah, blah. It's this stuff. Okay? It's some dye. It basically, it goes into the cells and then it can't come out. It reacts with something in the cells and it can't come out. Okay,
so what's between the cells?
So between the cells is an extracellular matrix of collagen fibers and these proteoglycans. So these are the charged sugar molecules. Okay? So they draw in water because of their charge. And so again, so the idea here is that if you look at the beginning, these cells move fast, and then towards the end, everything moves together. Okay, so in the beginning, these cells move fast, and then towards the end, everything moves together. And now the beginning, these cells move fast, and everything moves together. Okay? So the idea here is that automatically from a video like this, you can already tell that the tissue is not homogeneous, that right over here, there's a region which corresponds to, it turns out, where the collagen fibers are randomly oriented, which is much, much softer than the tissue above or below at very small strains. But then as you strain the tissue further, that region becomes stiffer, and then everything starts to move together. Right? So that's what you're seeing in a video like this. And you can quantify that, so you can, for example, use PIV to track the displacement profile as a function of depth, okay, in the horizontal axis. Then from something like this, you can take the local derivative and get the local shear modulus, or the local strain rather, and from the local strain you can then extract the local shear modulus. And so this is just telling you what you see, what you saw in the video, that near the surface the tissue is quite stiff. It took this massive dip right below the surface, about 100 microns below the surface, and then the tissue became stiff again as you went down further towards the bone, okay, in the bulk of the tissue.
These cells are dead, right?
No, the tissue is alive. Turns out chondrocytes are not vascularized, so they can survive for a very, very long time. They're like cockroaches. They just don't die. So then you can quantify further what I showed you in the movie, which is that if you take a look at that dip, as I go to higher and higher imposed strains, that modulus creeps up, and eventually that dip disappears, and you just have a region that's as stiff as the rest of the tissue. Okay, so that's what this part shows, and I think we have the statistics here. So if I plot the minimum modulus divided by the deep or plateau modulus, you can see that you get this very statistically significant difference between them for small strains. You can also show another experiment, which is that if you take the tissue and you first compress it, then this weak region actually gets deeper. So in other words, the weak region gets weaker. And so when you start to put all this stuff together, you come up with these thought models, and the thought model that we came up with was something like this, where the idea is that if you have fibers that are connecting the top of the tissue, they're parallel near the top, perpendicular near the bottom, and if I now start to compress the tissue, these fibers might buckle. And the idea is then that buckled fibers are very easy to strain, because if I have, I'm going to borrow Jacques' power thing here. So if I have some kind of fiber here, it's very easy to shear it when it's bent, but the minute you strain it enough so that they become taut, then everything starts to move together. Okay, so that's the idea behind the network here. Of course, our network is much more complicated, and we're going to need a lot of help from the folks who do these semi-flexible polymer physics type problems to try and figure out how this extracellular matrix of collagen fibers, which probably looks much more like this, with changing orientations and changing concentrations, provides you that kind of response in the macroscopic bulk tissue. Okay? So we did one other set of experiments that I want to tell you about. We looked at the frequency dependence, and now we only applied strains that were small enough so that we were in the linear regime. So we didn't go to high enough strains where the polymers were stretched. We just went locally and asked what's the frequency dependence of this tissue. And then we plotted that as a function of frequency for the minimum region, that weak region that I showed you, and the bulk region, the stiff part. And what we saw was that the stiff part was, of course, much higher in value than the weak region. But it looked pretty much like a plateau, and then a very small region over which you got a non-trivial frequency response, and then a plateau again. And so what this kind of curve tells you is that there's only a limited range of frequencies over which this region of the tissue is actually viscous. Okay, is absorbing, has a non-trivial loss modulus. Whereas if you take a look at the G-min, which is associated with that dip at 100 microns below the surface, it has a non-trivial frequency dependence all the way through, which tells you that the G double prime, the loss modulus for this part of the tissue, is again a substantial fraction of the modulus. Okay, so why is that interesting? Well, if you start to then ask about energy dissipation in the tissue, what that's telling you is that since energy dissipation goes like the loss modulus times the strain amplitude squared, this weak region ends up being where almost all of the energy is absorbed in the tissue. Okay? So yes, we know that cartilage absorbs energy and shocks that are applied between bones, but where in the cartilage is this energy absorbed? And the answer is in this weak region right below the surface. So why is that important? Well, because there's a lot of procedures these days that you can go into, that the doctors will do, to shave your cartilage and do some resurfacing. And if you start shaving too much, i.e. more than one hair's diameter, then you've pretty much gotten rid of this weak region, and you've set yourself up for later trauma, to your cartilage. So I think what this work is trying to get at is that there's quite a bit that we can learn from trying to look at the local mechanical properties, and we're going to need to understand the local mechanical properties in order to address how healthy tissue functions, and then say how diseased tissue functions differently, in order to then eventually come up with artificial tissues that we can construct in order to address these problems. I just want to say that once we started doing the articular cartilage, which is the cartilage of the knee, people started coming to us with all sorts of other cartilage. So this, for example, is cartilage of the spine. It's the intervertebral disc cartilage. I'll just show a couple of movies before I end, but the idea here is that you have a tissue which is composed of lamella. These are fibers that are oriented in pleats that are surrounding some nucleus. And the idea here is that when you shear this, in this particular configuration, you're shearing this way. And so if you can look at the little wavy lines in there, as I shear one direction, they straighten out. But the other side compresses. When I shear the other direction, this side straightens out and this one buckles. So there's this kind of double rope-like, mechanism. Why is this the way it happens? I have no idea. What about if you then take a look at a different orientation, where now instead of looking at it like this, I'm putting it down so that you're looking at fibers coming out of the board and fibers that lie along the board. So here are the ones that lie along the board, here are the ones that are coming out. And what we find is that in this configuration, only the fibers that are coming out of the board, my little fingers here, are absorbing any of the strain. Okay, again, a very non-homogeneous response. Why is this the best way of constructing a tissue to allow us to do, the various motions that we know how to do in order to attract the other sex and then reproduce and whatever? So again, the idea is that studying the local mechanical properties ends up being very important for addressing these kinds of questions. So I think with that, I'll end and just say that we're, I think, really just at the very tip of the iceberg, because pretty much all the tissues in our body are inhomogeneous locally, and so trying to understand something about them would be useful. Thanks.
That you put these things under tension? Have you put these under tension and then?
Yeah, so you can put them under tension if you have glue. Otherwise, we're always putting them under a little bit of compression. And with glue, you can put a little bit of tension.
And then does your thought model sort of...
Yeah, so what we did was we showed that if you... so we didn't do it under tension, we did it under compression. But the idea is that if you compress the tissue, then you buckle the fibers, and then you have to go farther in strain before you get the strain stiffening. And that part we get. Okay, the opposite, which is what you're suggesting, which is to pull it, you also should go a much shorter distance. Okay, so we do see some of that, but we've only gone through the compression part. We haven't done the tension. Meredith.